about for the new students who are here. A lot of interest in neutrino physics because of a certain quantum mechanical property of neutrinos called oscillations. And he will tell you about very different kind of oscillations here, these fast oscillations. You know, he's in a paper that has just come out recently. And I think you will take one look at the students and decide that you will give a nice introductory talk. Basudeb is very good at speaking, so I'm sure you'll all look forward to the talk. This talk will also be on YouTube, and I guess if there are questions on YouTube, then Arijit will handle that and ask the questions. So if you are confused in the middle about some notation or something, you can ask the speaker. Otherwise, please keep your questions for the end of the talk, okay? So, Basudeb.
So thank you, Shantan. Thank you, Indu. Thank you, everyone else, for having me over here. It's a pleasure to be back at Math Science. It's a real pleasure that I get to give a talk at the 60th year celebrations of Math Science. This is one of the first research institutes that I ever saw in my life as a KVPY student. I came here in 2001 or 2002. I spent about a month here. And after that, I decided that I would like to do physics. So I have fond memories of this place, and it's a real pleasure and an honor to be invited back to IMSC for such an important occasion. So the talk that I'll give today is based on some of the work that we've done over the last 5 or 6 years. It's been done with several students, and I'll mention them at the end of the talk. But let's begin. So something that's perhaps a little too painfully familiar to us, all of us, because of the experience of last 3 years, are exponential increases. You know, so things grow exponentially, and sometimes that's a good thing, sometimes that's a bad thing. Here are some examples. I don't expect you to read the details of any of this. What I'm trying to tell you is that there are a variety of physical phenomena where something grows exponentially. The top left is human population that grows exponentially. Oops, nope. Yeah, so that's the rise of human population over many, many years. The next one is the growth of the number of transistors on a chip. Again, that's growing exponentially. Sometimes these things look like a straight line because the y-axis is on, you know, a log scale. So I hope everyone here is familiar with that, that if the y-axis is logarithmic, an exponential looks like a straight line. This one is interesting. This is, you know, how a fire spreads. That also seems to be exponentially. There's some example from somewhere. And very famously, chain reactions, chain nuclear reactions grow geometrically, exponentially. All of these things grow exponentially. Now, yeah, very deliberately that example has been avoided. Yes. So the early growth of at least COVID-19, and you know, like many others, I was interested in looking at the data. It did grow exponentially early on, and I was tracking it for the first few weeks. And I think, so yeah, so the rate, you know, r to the power t, this r was 1.14 early on. So it was growing at like 14% compounded every day. Okay, so this is all fine. So many things grow exponentially, but what I want you to focus on is the two physical features of all of these facts. That it starts exponential, but then it stops being an exponential at some point. You know, there's a saturation effect. You know, things don't grow exponentially forever, and the reason is that some resource runs out. Okay, so this is very, very generic phenomena. Something grows exponentially and then saturates. The initial growth is exponential because the growth rate is proportional to the value of this object at that time. This is a tautology. If the definition of the exponential is the solution of some differential equation which obeys this feature, but still said in words, I think it means something. That if the rate at which you are growing is proportional to your current value, that's an exponential. And we will see that sometimes that's not what happens. You grow at some constant rate, your constant velocity. You put some gas into your car, your car moves at some velocity. But if you grow at a rate that's proportional to your current value, your growth can become exponential. This is what happens, for example, if your money is kept in an account that keeps getting compound interest. It grows by 10 rupees on 100 rupee in the first year, but then you get 1 rupee extra interest in the second year on the 10 rupee that you had acquired in the last year. All right. So this talk is not going to be about money or fire or pandemics or anything else. It's going to be about growth of neutrino oscillations, and I'll tell you what that is, in stars. And this growth that happens exponentially. Now, this is again a log scale, and you can see here as a function of time in nanoseconds. Now, this region is roughly linear. It's not exactly linear, but roughly linear. I'll show you better examples later on. And this is what I'll call exponential growth. I use the words instability here, and I'll explain that later. And then eventually it saturates. Once it becomes large, roughly order 1, and this thing can take a maximum value of 1. So that's why it's already beginning to saturate once it gets close to 1. But it doesn't always happen. So this red curve, is some other situation where the same system, under some other conditions, does not show this exponential growth. And this is what this talk is about, that exponential growth of neutrino oscillations inside stars. How does this exponential happen? Why does it happen? When it does not happen? And how does it saturate? Where does it saturate? The details of this saturation. So the beginning and the end. Okay. So why do we care about any of this? Let's start with motivation. So we care about this because neutrinos affect lots of astrophysical processes. Okay, that's the short story. In particular, for massive stars, how much heat is deposited at different parts of the star depends on which neutrino flavor, so there are 3 of them, nu e, nu mu, nu tau, which flavors carry how much energy. Okay? And so neutrino oscillations allows one flavor of neutrinos to become another, and that allows you to move energy from different parts of the star from one part to another part. And unless you understand neutrino oscillations, you cannot reliably predict how a star heats up, especially massive stars. And so that's why we want to understand neutrino oscillations in stars. Neutrinos also affect all kinds of nuclear processes when new elements are made. So in particular, we will talk about R process nucleosynthesis later on. And if you want to know how much of each element was made inside various stars and in the early universe, you need to know about neutrinos. And finally, we have now neutrino detectors that are capable of observing neutrinos from far away exploding stars. And if you want to understand the signal that you observe at your detector, you again need to understand the neutrino oscillation physics. So these are the practical, so to say, reasons for doing what I am doing. But there is also the theoretical aspect of it. There is, the fun aspect of it, and that's the following. So let's go back to our, first year undergraduate physics. So here is this equation. It should be familiar to you. What I'm showing here is that the time derivative of some quantum mechanical system, described by its wave function, let's say, is proportional to the energy of that quantum mechanical system times itself. So it's an eigenvalue equation, and this is the type of equation that tells you that this system evolves at a frequency that's given by this omega oscillation. Well, this is the standard kind of quantum mechanical problem that we solve. Now, this is for one such quantum mechanical system. What I will be talking about here is a set of coupled quantum mechanical systems. So there's not just one such neutrino, but there will be many neutrinos. There's a tower of such neutrinos. And the equation for any one of them will be whatever we had before, just omega oscillation times this, plus some new term, which looks complicated, but let me just parse through this. This term is a sum over n number of terms. Why? Because I assume that I am working inside a box of volume V, and there are n neutrinos inside it. Each of these is a neutrino, and the evolution of the ith neutrino depends on the properties of all the other neutrinos. J runs from 1 to n. What appears here, in this funny ket bra of the jth neutrino, is actually the density matrix of the other neutrinos. But if you don't know about it, just bear with. Just imagine that is some way of rewriting the wave function of this neutrino, and then there are factors that depend on the coupling between these various neutrinos, and in particular, this is 1 minus the angle between the momenta of the ith and the jth neutrino. And this G is just some dimensionful parameter. It's called the Fermi coupling constant, that when you do everything will give the correct dimensions. So here this has the dimensions of energy because you have a time derivative. Time derivative means the frequency, frequency is energy. So this term must also be of dimensions energy. In fact, all these other things are dimensionless, and this n divided by V is what gives you the correct. GF has 1 over energy square dimensions, and then together all of this becomes dimensions of energy in natural units. Now, the new thing that will happen in this problem, so in this problem relative to the standard neutrino oscillation physics, which I will explain to you again later if you don't know about it, is that unlike this problem, the oscillation frequency will become something that's proportional to n. That's bizarre. Okay? So if that doesn't strike you as bizarre, let me tell you that that's bizarre. What I'm saying effectively is that this is a bit like a simple pendulum which has some frequency. Now I'm saying that I couple n number of simple pendula, and the oscillation of these n number of simple pendula happens at a frequency that grows with however many simple pendula I put in this congregation. That's bizarre, right? I mean, if you have any intuition about how things oscillate, that's not what happens usually. So we want to understand why this can happen and what is required to get this truly unusual behavior. And then the question that, okay, so it starts with this exponential growth of these oscillations, which is very fast because it's proportional to the number of agents in my box. What happens to it at late times? Like, what happens to these oscillations? Do they stay coherent? Something else happens? We want to know that. So beginning and end, these are the two questions. All right. So that's the pre-introduction, and then I'll come to the real introduction after this. But any questions at this point? No? Okay. All right. I'll proceed. Okay. So neutrinos are elementary particles. These are elementary particles in the same way as electrons, except that they have no charge. They come in 3 varieties. So there's nu e, nu mu, nu tau. They're given these names because these are associated with the charged particle that they're produced with, let's say in W boson decay. So just 3 kinds of neutrinos. They don't have fixed masses. These neutrinos don't have fixed masses, but in some way you can imagine that they're very light, and they're lighter than 1/1,000,000th of an electron mass. They interact weakly, by which means that they interact, let's say, at a rate that is 10/1,000,000th compared to 1,000 compared to, let's say, electromagnetic interactions. And this is the most interesting part, at least for today's talk, is that unlike other particles, you have an electron is an electron is an electron. It just stays an electron forever until it dies, something happens to it. Neutrinos are not like that. They are shape-shifting, objects. So you have an electron neutrino. After some time, it can become a different neutrino, a new muon neutrino, a new mu, for example. This is called flavor oscillations, and I'll tell you how that happens. Okay, but one thing to keep in mind is that this has been going on for 3, 4, 5 decades. We now know that these neutrinos exist and that this phenomenon of neutrino oscillation is not just experimentally verified, but experimentally established to an extent that it's almost universally believed to be correct. And many detailed features of these oscillations, these standard neutrino oscillations that I'll explain to you in a minute, have been checked. So let me tell you what neutrino oscillations are. So you have a 2-component quantum mechanical system. So, you can think of these 2 objects as the amplitudes of being in any one of the flavors, of being in the nu E flavor versus the nu mu flavor. And these amplitudes change with time, described by this differential equation. Okay, and this matrix, this is a 2 cross 2 matrix that's multiplying my 2-component wave function that describes how each of these amplitudes is going to vary with time. So if I solve this equation, what I'll find is that I start by being in, let's say, one of the states, let's say electron neutrino. Let's follow this red line. As a function of time, my probability, which is the mod squared of this, roughly speaking, is going to decrease with time sinusoidally, and then again increase back, and it keeps oscillating like this. These oscillations happen with a frequency that's related to this factor that's up front, which I've written as delta m square over 4e. This is the difference of the mass squares of the 2 eigenstates divided by the energy of the neutrino. So that tells you that different neutrino energies oscillate at different frequencies. In particular, if the value of E is large, that means omega, the oscillation frequency, is small, okay, and that's this red line. If the value of energy is small, the oscillation frequency is large, and that's this blue line. So different energy neutrinos oscillate at their characteristic frequency. And this angle theta basically describes the depth of oscillations. And that's the description of standard neutrino oscillations. It's a 2-level system prepared in a non-stationary state, and then as a function of time, the probability of being in the original state oscillates sinusoidally with time. So you've done this in your quantum mechanical courses. In particular, this phenomena is also affected by the medium that the neutrinos travel in. And so in particular, this angle theta and this frequency delta m square over 4e can be changed because of the forward scattering of these neutrinos on background electrons in particular. Okay. So one simple way of looking at neutrino oscillations is this pictorial representation, which I like very much. So instead of a quantum mechanical system, we will think of a classical system that shows exactly the same behavior as this quantum mechanical system. So what I have in mind is this. So everyone is familiar with this equation, that the time derivative of some 3-component vector is some other vector cross this vector itself. This is the spin precession equation. Okay, so you have a spin p and it's precessing around the magnetic field B. This equation is mathematically equivalent to the equation that I had shown you before. So one can use the following picture, that the neutrino starts out by being in its original state pointing up with an intercept of 1 on the vertical. And the Hamiltonian that describes neutrino oscillations corresponds to a fake magnetic field which points in some other direction at an angle theta. Now my original spin is going to precess around this magnetic field at a frequency omega that's related to this delta m square by twice e, and the depth of oscillations is going to be given by the angle at which the Hamiltonian is misaligned with respect to the original neutrino. Okay. And so this is the physical picture. So now let's forget about all the quantum mechanics that we ever have learned and stick to this visual metaphor, that neutrino oscillations are about flavor pointing in one direction, and then they just basically precess around the Hamiltonian. This is the story of a single neutrino. Okay, now we are going to change this story a little bit. As I told you, one way to change this story is to change the mixing angle and the rate at which this precession occurs. And that's what happens if you just add some electron density in the background, and that changes your delta m square and theta in matter. The subscript m tells you that these are the oscillation frequencies and oscillation angles in matter, and there's some way of computing it. Don't have to worry about these details. Key point is that the rate at which the oscillation happens and the depth to which the oscillation happens, these get affected by the density of the background matter. An interesting thing happens when some of these terms cancel and so on. There's some interesting physics there, but let me not go into that. That's very important. If you're ever going to do neutrino physics, this is the stuff that you will spend your time on. But let me skip. What I am interested in today is what happens when there are lots of neutrinos in a box and you have to treat all the other neutrinos as a background to any one of the neutrinos that you are tracking. So one of your favorite neutrinos is oscillating, but this is oscillating in a medium of lots of other oscillating neutrinos. How do you solve this problem? So now I provocatively ask, can you just take this existing formula and add a term where instead of square root 2 g Fermi times electron density, you just replace it by the neutrino density and we are done? No, that does not work. And the reason it does not work is, unlike an electron which always stays an electron, the neutrinos are themselves changing flavor. So what exactly are you going to add here? You have to add a matrix. You have to add a 2 by 2 matrix with the 2 flavors. If you are working with 3 flavors, then it will be a 3 by 3 matrix. So you have to figure out some way of solving the problem where you don't add the number density of neutrinos, because that is not the physically relevant quantity, but the density matrix of the neutrinos in some way. So that's what we are going to do. Let me see. This capital N? I didn't tell you about that because I skipped over. What I was saying is that oscillation frequency depends, as you can see, for large electron density, this will be just proportional to the NE. NE is just number of electrons divided by volume. So you can see that the oscillation frequency just grows proportionally with density as N. And then you can check that the mixing angle that becomes. Yeah, so the small n is the density, that's capital N divided by capital V in some box. Okay. Now, what we are going to see is that when you add a background of oscillating neutrinos to any to this neutrino oscillation problem, the final phenomenon is completely different. So previously I told you that different energy neutrinos oscillated at their characteristic oscillation frequencies. Now they will all oscillate with the same frequency. So this is why I call them collective. They oscillate collectively. So that's what I show here in this cartoon. Not only do they oscillate collectively, there are modes of flavor oscillation which don't depend on the mixing angle in any way. So as I showed you in the previous slide, I think, if you have a large matter, this NE is large, then the mixing angle gets suppressed by 1 over n square. Sine square 2 theta gets suppressed as 1 over NE square, roughly speaking. So mixing becomes small, yes.
Making some kind of a mean field approximation, because in principle, you will have n coupled equations, right? Because they are all going from one to the other. So by making it an equation in only one flavor and taking that density into account, are you making an approximation,
Yes.
like mean field?
when I explain, I am explaining it as if I am making that approximation, but when I do the calculation, no such approximation is made. So it's just to give a picture of what's going on. I focus on any one of them, but imagine that I do it in a self-consistent way that I don't actually specially select out any one of the neutrinos. So this is mean field in a quantum field theoretic sense, but not mean field in the sense that some common evolution is assumed for all the neutrinos. No, that's not done. But it's mean field in the sense that certain it's a bit technical, but certain correlators are assumed to be 0 in quantum field theoretically. But that's for later. Okay, so one of the new things that happens when you add this neutrino background is that things can oscillate collectively. The other thing that can happen, and this is the crucial one, is that you can have oscillations that are large in amplitude even when the mixing angle is insignificantly small. Normally, neutrino oscillations have a depth that's given by theta, the mixing angle. But here, even when mixing angle is very, very small, taking the limit to 0 even, you get large oscillations. This is related to an instability, and so the picture that you have to keep in mind, and we'll come back to this later, is that previously you had these oscillations and the depth of the oscillations depended on this angle. Now the classical mechanical analog of these complicated collective oscillations is an inverted pendulum. That you've started with a pendulum that's pointing up, and it doesn't matter what your initial misalignment is. Even if it is insignificant, it will just come down. And so you will get full amplitude oscillations even with insignificant initial misalignments. And that's the instability, and we'll talk about that later. But the other thing here is that the frequency of these oscillations is not delta m squared by twice e. This can be square root of this omega times the new frequency that's G Fermi times the neutrino density, roughly speaking. The scale is square root omega mu, which can be much, much larger because the neutrino density is very large. Or it can even be just directly proportional to the neutrino density with no dependence on delta m square. And now all the experts who know neutrino physics should, balk at this idea. How can you have neutrino oscillations that don't depend on delta m square? Because if delta m square goes to 0, there is no difference between the flavor and the mass basis. So the answer to that is that no, you can't set it to 0 exactly. Take the limit, from above. So the bases are different, but the frequency of oscillations to leading order does not depend on delta m square. It's linearly proportional to the neutrino density itself. So these are the new phenomena that occur. And so again, just showing you a gallery of the kind of phenomena that will occur once you put this neutrino background. This is called synchronized oscillations. So here you see the what is on the x-axis is omega times t. Okay? So you can see these oscillations of the different lines at different energies. They've all gotten synchronized, same frequency of oscillation roughly speaking, and they're all oscillating together. This one is square root omega mu times t. Mu is something that's proportional to the neutrino density. And now you see I have these oscillations which are not quite sinusoidal oscillations, and they're happening over a time scale that's inversely proportional to square root omega mu. And then these are the fast oscillations, which is what we will talk about in this talk. Okay? Again, no dependence on omega, just mu, just the neutrino density. Order one-sized oscillations. What's being plotted on the y-axis is, let's say, survival probability. Probability that a neutrino stays in its original flavor. Okay. Just to revise the differences between ordinary and these fast collective neutron oscillations. Ordinarily, survival probability looks like this, for a simple two-level system. 1 minus sine square twice of the mixing angle, sine square delta m square by 4e times time. This delta m square by 4e is the oscillation frequency. So at the beginning, let's say when we take the t goes to 0 limit, this sine square term can be replaced by just something that's proportional to t square. And for small mixing angle, let's say because there is a large background density which has suppressed my mixing angle, this sine square twice theta can also be basically replaced by something proportional to theta square. So you see that the survival probability changes away from 1 quadratically with the mixing angle and quadratically with time. And this is what happens for ordinary oscillations. What we will find now with fast collective oscillations is that this will not be quadratic in time, it will be exponential in time. And now this we can appreciate that there is a big difference here. Not only will it grow exponentially with time, it will not depend on theta at all. It will be non-zero in the limit theta goes to 0. And it will not depend on delta m squared by twice E either. It will only depend on the neutrino density. The rate will be G Fermi times neutrino density. It's much faster. It's very unusual stuff. At late times, what happens to this? At late times, you average over this sine square delta m square by 4E times t term, and you average this to half, and you get a steady mixing of the flavors dictated by just the mixing angle theta. And this is the late time limit of this survival probability. And we know this is the kind of thing that applies to, for example, solar neutrinos. And we would like to be able to derive the equivalent formula for fast collective oscillations, except that we don't have an analytical solution, so we can't quite do this. So how do we do it? Okay, so these are the two problems. So to first tell you about the beginning of fast collective oscillations, and then about the end. Exponential of, so t has dimensions of time, so you need something to yeah, exactly. So that's the mu, which is G Fermi times neutrino density. So we will find that it grows as exponential of Fermi constant times neutrino density times time. Thanks. Okay, so now to the real world. Oops. Okay, so the situation that I should have in mind is the following. There's a star, there's an exploding supernova. Neutrinos of different flavors, here represented by the 3 different colors. So blue are the electron neutrinos, the reds are the electron antineutrinos, and the other neutrinos are in green. The reason for this choice of separation is that in a supernova, the typical temperature is around 30 MeV, 30 mega electron volts. At those temperatures, you can't typically produce muons or tauons. So new mu's and new taus and their antiparticles behave roughly identically. So we club them into a single bucket, and let's call them other neutrinos. Those are the green ones. Nu e's and nu e bars are slightly different because the neutron to proton ratio in the star is not 1. So they have slightly different properties. So we'll have 3 neutrinos, 3 kinds of neutrinos: nu e's, nu e bars, and the others. They are initially trapped inside the star, and then they slowly diffuse out. At some point, the density becomes small enough that they can start free streaming. In the middle, they oscillate, and then they are finally detected at Earth. Typically, they start free streaming at a distance of around 10 kilometers from the center of the star. And in this region between 10 kilometers to approximately 100 kilometers from the center of the star, all these complicated oscillations will happen. And that's the theater on which now I have to analyze the flavor dance of these neutrinos. This is also the region where the star gets heated up by the escaping neutrinos, and that's what is eventually responsible for the explosion of the star. Okay? So calculating the flavor evolution here is very important from that perspective. This is also the region where different elements are created depending on the abundances of the various neutrino flavors, nu e's, nu e bars. And so therefore, again, we need to know how many of these neutrinos there are. And of course, we will detect neutrinos here at Earth, but we are going to detect neutrinos not as they were produced, but after some amount of processing that happens here. So the relative ratios, the abundances of the different flavors would get changed because of neutrino oscillations, and this weird kind of neutrino oscillations, not the standard ones. So if we want to decipher the information that these neutrinos are carrying, it would help to know what happens in between. Then we can undo the effect theoretically and therefore discover the true primary initial conditions inside the star. So these are the three motivations for studying this. Technically, this is how we study this system, just to kind of give you a flavor of the kind of equations that we need to solve. On the left-hand side is the density matrix of any one of the momentum modes of the neutrinos. So the rho is a density matrix. P is the momentum mode for which I am writing down the density matrix. And what's operating on it is not just the time derivative, but the full Liouville derivative. So del T plus velocity dot spatial gradients. So this is the d by dt. On the right hand side are commutator of Hamiltonian with the density matrix. So the first term is the usual neutrino oscillation term. The next term is the effect of background matter. And this third term, again, this should be familiar to you based on the cartoon equation that I had shown you before, is the commutator of this density matrix with all the other ones. You see, this is P, and then I have a sum over all the Q's, and there is a coupling between the P and the Qth neutrinos proportional to G Fermi. This is exactly what I had shown before. Previously, I had the divided by V here, and that's because at that time I was talking about individual neutrinos, and now I have talked about density matrices. So that takes care of the dimensions. Okay. So this last term, we can think of it as having a rough size, which is G Fermi times the number density. So if we didn't have all this complication, and if we were just going to do an integral d3q times rho q, we would have just gotten the neutrino density, momentum integral over all momenta of the neutrinos basically just gives you the number density of neutrinos. So that's the scale, the new scale in the problem, the collective potential, G Fermi times neutrino density. This is the scale that will be much, much larger than omega, and this is what will lead to the fast oscillations. So, and this is also the term that's going to make the problem collective. Just to give you a little bit more intuition about why it will make things collective, I told you about this picture of the precessing spins, right? So there's a spin that's precessing around a magnetic field that's described by the mass mixing Hamiltonian term. But you might also have this intuition that every spin is actually a tiny magnet, right? So every spin exerts a magnetic field on all the other spins. So now imagine there are lots of spins. That's what these different neutrinos are. They're all sitting very close to each other, at the same point, in fact. And now each of these neutrinos is precessing around the magnetic field, not just given by this, but by the sum of all the other magnetic moments of the other neutrinos. Of course, these are fake magnetic moments, not quite real magnetic moments. These are the flavor moments, if you will. And so what happens is that one way that this system can react is that it gets locked, pinned in together, and then they precess at some average frequency. That's synchronized oscillations. But there are other modes in which this system can evolve. One of them is that if initially some of the spins are up, pointing in one flavor, and some of the spins are down, pointing in the other flavor, then they can swap flavor, maintaining certain conserved quantum numbers. And this dynamics can happen at a rate that's even linearly proportional to mu. And that's what fast oscillations is actually. Yes? This term? Yes. what will actually change is the sign of this term. So, yeah. So if I write the same equation for rho bars, everything will be the same, just this term will have a minus sign. No. No, that's only one of the, relatively they have to change, Only one of them change, and I will choose to make this one change. Yes. So your question is that oscillations are periodic. How am I getting an exponential? So if you remember that for the ordinary case, I showed you that the early part of the periodic oscillations is a quadratic. So when I say exponential, I mean exponential initially. And what I want to know is that what is the analog of the sinusoid, which I have to admit I can't tell you, I don't know the answer, but I will be able to give you the late time average of the sinusoid. Instead of the half, whatever else we get here, that I can calculate. So that's the end. Okay. Okay, so what starts collective instability, what starts it? That's the beginning. And so now this is a proof that we just did a couple of months ago. The answer is as simple as this, that if you draw the momentum distributions of the different flavors and they cross at some point in momentum, so go to any physical point in the star and say that, okay, draw the momentum distributions of the nu e and the nu e bar and the nu mu. Do the momentum distributions cross at a point? If yes, there will be instability. So this is the statement. So what starts fast collective instabilities? This crossing of momentum distributions. So this is the theorem. Okay, so I will not give you the proof of the theorem. I'll give you a sketch of the proof in a minute. But rather than give you the proof, let me first tell you what it means to have this crossing. Okay, so that we will do in a second. See, the different flavors, nu e, nu e bar, and the others have different cross sections. Because nu e's and nu e bars have both charge current and neutral current interactions, and this has only the neutral current interactions with electrons in the background. And these two are different because protons and neutrons are not in the same abundance. Also, given that we have only electrons and not positrons in the star, cross sections are different. In fact, this has the largest cross section, these have the smallest, and this is somewhere in the middle. Whatever has the largest cross section will decouple from the star the latest, at the lowest density. But that is where the temperature is smallest. So you can guess that the electron neutrinos will have the smallest average energies. Whereas the other neutrinos, the green ones, will have the largest average energies because they have the least interaction. They can decouple deep in the star where the temperatures are higher. So therefore, if you look at the energy spectrum of these flavors, you will find that the other neutrinos have a hotter spectrum, higher average energies, whereas the electron neutrinos have a lower average energy, and then they will cross somewhere. Okay? So this is the reason why the energy distributions can cross. Similarly, and this is the more interesting one, the angular distribution of the neutrinos at any point in the star are also different, and they depend on flavors. So consider this point where the electron neutrinos have not yet decoupled, so their angular distribution is very isotropic, whereas the other neutrinos have already kind of decoupled, so their angular distribution is more forward peaked, going out, this is the direction outside of the star, and their angular distributions is going to cross. So this is also a crossing of the momentum distributions. They cross here and here. Okay? And this will give the collective instability. In particular, these kind of crossings give instabilities, collective evolution, which grow at a rate square root omega times mu, and these ones grow at a rate that's proportional to mu. Okay, and how? Let me just show you that. So this is the sketch of the proof. So first you linearize the equation of motion. So there is some equation of motion like this equation that I showed you in terms of matrices. You linearize it. So we are doing a stability analysis. And then you ask for this linearized variable, is there any Fourier mode that grows exponentially, which is to say that if I write it in terms of Fourier modes, is there an imaginary frequency? Okay. Turns out that this demand of an imaginary frequency requires a certain matrix to become non-positive. Not surprising. Usually when we want, let's say, frequency to be imaginary, we are saying that, okay, something is omega square is negative or something like that. The same thing here. And this matrix is something which has elements which are integrals, which are the difference of the phase space distributions of the two flavors. Okay? So then it turns out that the non-positivity of this matrix, which is what is necessary for this exponential growth, gets related to the fact that the difference of the phase space distributions is not of the same sign everywhere in momentum space. Somewhere it is positive, somewhere it's negative. That means at that point there is a crossing. And so that's the proof. Okay. So now I don't think, so this is the proof, so I think it's best avoided. If you want, I will come back to it later. Okay. So that's the beginning of the fast collective oscillations. The fact that if you have a bunch of neutrinos in a box, each neutrino exerts an influence on the other ones, and the rate of oscillation of each neutrino gets affected by the other neutrinos, and this all needs to happen in some self-coupled way. There are ways in which this oscillation can initially grow exponentially, and the reason for that is that in momentum space, the phase space distributions of the different flavors cross each other. So that's so far, yes.
See, when you have this collective instability, you are also talking about the temperature, which means you are assuming some kind of quasi-static equilibrium. How is that going
Okay,
to affect?
so this is a little maybe imprecise vocabulary on my part. So the temperature is of the medium from which the neutrinos have now decoupled. They have a momentum distribution which is their memory of the time where they were in thermal equilibrium, but now they are not in thermal equilibrium anymore. So their initial conditions carry an imprint of the last time they were in thermal equilibrium, and that's the temperature that I label them with. But great question, thanks. So let's move on in the last 10 minutes. Yeah.
So these densities, because as they stream out, your densities are changing, right? And as the interaction goes on and you have flavor swapping, again your density distributions are changing.
Yes.
So that is built into the dynamical solution.
Yes. So you would have to take into account that the neutrino density is dropping, and that would go into that third term, because the effective normalization of those rows is going to change in some way.
So when the swap occurs, then you're completely
Yes, exactly, and that's why this problem is hard. So basically you're solving millions of partial differential equations coupled to each other. You see, the left-hand side had a time derivative and 3 spatial derivatives, and the right-hand side had an integral over the 3 momentum directions. So this is a 7-dimensional partial integral differential equation. Yes.
Maybe a very naive question, but this business of linearization of that equation, that is okay if you do a small enough time interval.
Yes.
That is
Yes.
protective.
Yes.
It's not doing any major
No. So in fact, indeed,
outcome.
indeed. So the point of this linearized analysis is to simply diagnose the instability. And that's all that it can do. It can say that, is there an instability, is there not? If there is an instability, how fast does it grow initially? Beyond that, this linearized treatment cannot tell you anything. And that's why the next part. So what happens at the end? So to track the full solution is very hard. So there are, I think, very few cases where one has the full solution. In the slow instability case, where the instability occurs because of a crossing in the energy distribution, not the angular distributions, and the oscillations are proportional to square root omega times mu. In those cases, there are some analytical solutions, and what happens at late times basically is that imagine that there was this black energy spectrum, which is this tall one, and this red one, which was the short one, and which had a crossing here. What happens at the end is that parts of the energy spectrum around that crossing have gotten switched. Do you see that? So imagine that you initially had a black spectrum that looked like this and a red one that looks like this. These are the two flavors. They would have a crossing here, and around this crossing you go on both sides and you exchange the flavors. Okay? So that's the final effect of the slow oscillations. Yes, this can be exactly solved. This is, I'm just not showing you the exact solution. I'm just telling you the answer. Yeah. This is something that one can do exactly. Yeah. So similarly, for the fast case, which is, because of crossings in the angular distribution, this is the toy model. So the toy model that you can solve is a model with 4 momentum modes. So you imagine that there are 4 momentum modes, and for each of these 4 modes you write your equations. You do some manipulations where you redefine these 4 modes L, R, L bar, R bar in terms of some 4 new vectors. Basically it's a basis transformation. And then in this basis, this vector Q has this equation, which you can then show derives from this Lagrangian, where you identify this part as the potential and this part as the kinetic energy. So you go ahead and just plot the potential, and you find that the potential is actually a quartic potential like this, and you're starting somewhere here. And for the cosine of the angle between the modes larger than 0, we start with the potential like this, which you roll down. And if it's like negative, then you start with a potential that's inverted, and you start here, and you don't have an instability. So this is a case that you can solve exactly. And in this case, again, there's only one scale in the problem, mu, the only frequency in the problem. So all the dynamics is fast. So this is one case. Yeah. So this is the work of Manibroto Sen, who did a PhD at TIFR with Amol and me, and this is part of his PhD work. Okay, but this is a very simple case. In only time you forget about space, and real toy problem, if you will. You get a lot of insight, but we also want to understand what happens in a more realistic case. And that's very hard. As I described to you, it's a 7-dimensional problem, partial differential equation. It's a horrible mess. But you can't avoid that mess. Turns out that you have to work in one spatial, one momentum, and one time dimension to get any sensible answer. And the reason is this, that the crossing is in the angular distribution. So you have to keep space. Otherwise, like what are you doing? Crossing is in the relative abundance of the different flavors in different directions. So you have to have direction. Okay, so that's why this is the minimum that you can do. So we start numerically. Okay, so this is 1 plus 1 plus 1 dimensions. So one space, one momentum, one time. And so this is the numerical problem. So we start with a one-dimensional problem. At each point in my box, it's a periodic box, I let neutrinos go in all directions. Of course, there is no direction up there, right? This is just pictorial representation for the velocity, which is along this only one spatial dimension that I have. And what I'm showing here is that the 2 different flavors, the blue and the green ones, they cross somewhere. So the velocity distributions cross each other at each point. And then I let it evolve in time. Okay, so that's the problem. So this is the thing that captures the flavor evolution. Del t plus v del z acting on it is something that depends on the relative difference of this phase space distributions times the cross product of these vectors. So you solve this problem. What you find is this interesting thing, that here is time on the x-axis and the one spatial dimension that I have on the y-axis, The actual box that I've solved is much larger, and I'm only showing you a small section of it for you to be able to visually see the features. The box is actually 5 times larger than this. So for the first 4.5 or whatever, 3.5 picoseconds or so, so the parameters are chosen to reflect the values inside the star. So first 3.5 picoseconds or so, the neutrinos don't do anything. They just stay where they are. The flavor is not changing. And then you see that there's this stripe, which means that the neutrinos have tipped down and changed flavor collectively, and then there's a next oscillation, and it happens over a time scale that's basically picoseconds. And this is basically, you can check the frequency that's given by the G Fermi times the neutrino density. But what happens after 3 or so, 2.5 or so oscillations is that everything gets jumbled up, and there's decoherence, dephasing of the oscillations. Okay? This is the equivalent of this sine square term averaging to half, except that now I don't have a sinusoid, so I don't know what it averages to. I mean, I know numerically now, but this is the thing that now we will compute analytically. Okay? So one thing that we already notice there is that initially the flavor evolution, if I do a Fourier transform of this field along the spatial direction, I will get only small k modes. It has large wave numbers only. I mean small wave numbers, large scales. But later on, it becomes very patchy and very granular, which means that power is somehow flowing from large scales to small scales. In this, the power in the flavor field is diffusing to small scale. So there's a cascade, which is also shown here. So you start with something that has power only at, let's say, k around 8 or so, and then as time goes, suddenly around 2.5 picoseconds or whatever, you start populating all the other k modes, and eventually you have populated all sorts of k modes almost democratically. So this is again numerics. Yeah, so as you go from bottom to top, these are later and later times. The power in some Fourier mode of the kth Fourier mode of.
What does the box stand for?
This is the amount of flavor conversion, because I'm only computing that how far away from the vertical I am. That's what computes flavor conversion. But not only in space, there is diffusion in momentum space also. So initially, all the momenta are very collective. But over time, the momenta start dephasing with respect to each other. The different neutrino momenta, the different velocities, they don't all oscillate together. And that's what's shown here. This is the phenomena which we were able to massage our 1 plus 1 plus 1 partial integral differential equation into first a partial differential equation by doing an integral transform, and then using a scaling variable we were able to convert it to an ordinary differential equation, which we were then able to solve. And this is that ODE, so this is the PDE, and then you will notice that there is a scaling that everything must only depend as a function of n square by t or something. So if you take n and replace it by n squared times a and t as t times a, this equation will remain invariant, and then you do some massaging, you figure out that there's an analytical solution to this equation, which describes this flow of power to higher multiples, which explains this decoherence. This, if you are then going to coarse grain over the small scales, is going to give dissipation or relaxation in the problem. And that's what you see, that all these different colors are the different velocity modes, and at late times, some of them go and settle down here, some of them go and settle down here. Only a very few modes stay stuck in between. Okay? So as a function of time, you start here, some of them go and sit at a different point, some of them go here. Ignore the right hand plot. Yeah, for both, but slightly different thermal distributions for the two flavors. Okay. Okay. So anyway, point is that again, this is analytically predictable, not worth going through the derivation. It's just there's some way of doing it. Just like how we can do it for 4 momentum modes, there is a way to do it for infinite number of modes, and this is the answer. So, and what you see here, these are like many different calculations. All the dots are numerics. All the blue straight lines are our analytical predictions for this problem. And that prediction is just, for all these 4 places, is just this expression. And every single parameter that appears here is known from the initial conditions. So it's just, integrable problem. Okay. And as a result of that, we are able to predict as a function of velocity what is the final survival probability. This is 1 minus survival probability as a function of the momentum variable. And we are going to average over space, because we are going to basically coarse grain over centimeter sized regions. And then this is the dashed are analytical predictions, the solid are numerical calculations. Okay, again, pretty reasonable agreement, I think. Okay, so this ask me later is a provocative slide. Anyway, so let me finish now in the last, couple of more minutes maybe? Okay. Why? Okay, so I have told you that neutrinos in a supernova, they start oscillating exponentially at a rate that's linearly proportional to the neutrino density. And then eventually, after a few oscillations, they decohere, and you get some sort of a steady mixing of the neutrino flavors. That is velocity or momentum dependent. Unlike this 1 minus half sine squared twice theta, here now we get an answer that was velocity dependent. Of course, you can average over this and get an answer that's not velocity dependent anymore, but it will still not be 1 minus half sine squared 2 theta, because this answer doesn't even depend on theta. But whatever it is, this long-term neutrino mixing can now be computed. And this is the thing that is relevant for, let's say, astrophysics calculations or observations of neutrinos on Earth or nucleosynthesis. So these are the 2 things that I've told you, but let me finish with why do all of this. Why we do all of this is because neutrinos can be observed. They exist, they can be observed. We've seen them already. And we expect that over the next maybe decade or so, there are many neutrino detectors that are capable of seeing these neutrinos, and we will see the impact of these oscillations in the neutrino signal at Earth. That's one of the first things that we expect to do. Not only this is just an example of what one can do with, let's say, super K or super Kamiokande detector, but let's not go into that. The other thing that I told you about is that the heating, so this is the Q plus is the heating due to neutrinos, depends on the neutrino luminosity. Okay. And this heating due to neutrino luminosity depends not just on the neutrino luminosity, but on the flavor dependent neutrino luminosity times the cross section. That also depends on the neutrino energies. If you have neutrino oscillations, this heating rate total summed over all flavors will be different. And now I have just shown you that there is a mechanism to do neutrino oscillations very deep in the star. So one has to calculate this. It's not yet done. It's an interesting problem. We had just at maybe 10 years ago, 11 years ago, we just said that if there were some magical mechanism which allows such neutrino oscillations to happen, what we had shown was the enhancement of heating can be approximately a factor of 2. Now, that we had shown many years ago. At that time, we did not have a physical mechanism that allowed such things to happen. We just said that, okay, if there were such a thing, now we have such a thing. Now we have to plug that into a supernova simulation and recalculate this and see roughly how much our true predictions differ from this. Okay, so that's the second thing. And finally, and this is the most interesting thing as far as I'm concerned, is that all of this goes beyond supernovae. These kind of neutrino oscillations can also happen in merging neutron stars. And the conditions are slightly different, but roughly the story holds. There are lots of neutrinos, and the neutrino oscillations are affected by the presence of all the other neutrinos. And merging neutron stars are something that now are of great interest to astronomy. We saw this gravitational wave event 170817, and there was an electromagnetic counterpart. So we know that these are merging neutron stars. And the light curve, the optical light curve of this event has been modeled by astronomers, and they have tried to figure out which elements must have formed in what abundance in order to produce the light curve that we actually see. So, it was initially very blue, became red later on, and this requires a particular sequence of heavy elements to be produced in the right abundance at the right time. This delicate requirement can prove a very interesting test for the kind of physics that I talked about, because these neutron oscillations will happen there as well, and they will affect the production of the various elements. So, as we know, almost all elements in the periodic table, with the exception of just the lightest ones, are produced in stars. The ones in blue-green are in supernovae, and the ones in yellow-orange are in merging neutron stars. So, almost all elements are produced by either massive exploding stars or merging neutron stars. And especially the heavier ones are greatly dependent on the neutron abundance. So, this is the ratio of certain elements, and it depends on the neutron abundance, and the neutron abundance can be shifted if you add electron neutrinos or antineutrinos, and which is basically what oscillations do. So, neutrino oscillations can affect how elements are created in stars, and this is one of the sample calculations. So, the blue and the black lines when you have few neutrinos, the red one is when you increase the number of neutrinos. This is N, this is Z, and this is the usual stable elements, and this is how the production of rapid neutron capture element changes because of neutrinos. This is just one sample calculation. Similarly, there's this other calculation much more recent, which shows that for mass number 140 and above, your abundance of various elements can be affected by whether you have these fast collective oscillations or not. So, the yellow is with something which is similar to fast collective oscillations, the green without, and you can see that there is a big impact. So, again, these are very preliminary. We still don't have enough data to make a robust comparison, but we're just starting. Okay, so let me finish here. We expect things to improve over the years, and let me summarize. What I've told you is that usually neutrinos oscillate using this very simple Schrodinger-like equation, and the frequency of oscillations is delta m squared by twice E, which is about once per kilometer for neutrinos of energy 1 MeV. In stars, in merging neutron stars, in exploding massive stars, because of the presence of a large density of neutrinos in the background, which are themselves oscillating, something new happens. And that new thing is captured by this complicated equation that I had shown you before, and I just show it again to remind you. And this complicated thing, what does it do? It allows fast collective oscillations, collective meaning all energies, all momenta together, at least initially. Fast meaning the frequencies are not once per kilometer, but once per millimeter, okay? Putting the real numbers. Exponentially growing early on. When is this possible? So, the beginning, what causes it? Crossing of the momentum distributions of the different flavors. What happens at the end? Large amount of flavor mixing, large amplitude flavor mixing, even when mixing angle is small, leading to eventually some kind of depolarization or dephasing or decoherence. This affects the heating of the star, creation of elements, and the signal that we see. Okay? So, that's all I had today. This work was done largely with Manibroto, who finished his PhD around 2017-18, and then recently, so the numerical work on 1 plus 1 plus 1D and the analytical follow-up thereof was done by Shomo, who's a graduate student who finished last year. I didn't have time to talk about the very nice work by others, but I take the opportunity to thank them as well. Much of this work was only possible because of very generous computing provided by all these grants and our support staff at CIFR. Okay. Okay. So I'll leave you with these questions. So. Okay.
Thanks, Basudeb, for an excellent talk on a very complicated and technical subject. The floor is now open to questions. Any questions? Yeah, just I'll pass this.
So, when you have this late stage, when you see this small, big, large scale coherence dropping to small regions of coherence, is this some kind of like a turbulent behavior? Do you see some critical exponents corresponds to this late time behavior?
You haven't checked. So, this is an excellent question, and I know of one paper which tries to make the analogy with turbulence. We didn't quite go in that direction for two reasons. This was already quite hard, and my interest was in just finding out the answer, like that what is the survival probability, because that's the thing that matters to astrophysicists. But that does not take away from the fact that what you have asked is interesting and important, and one should look at it. It's just that I haven't done it.
And sometimes these critical exponents of the turbulent spectra is related to some conservation laws. So
yes. So the way we derive that answer is to use the conservation law very cleverly without having to worry about some of the more formal technical stuff.
So you use this conservation of the momenta of this.
Yeah. So we use lots of conservation laws, but perhaps in a more pedestrian way. We focus.
Also, too many species floating around to look at critical phenomena.
I don't know, but
Interacting.
yeah, but one can look at, for example, how this coherence changes as a function of time, and if it changes in some very discontinuous way as a function in terms of some parameter, and then one can do a scaling analysis and try to figure out some kind of critical exponent. Yes, this is interesting stuff. If I were, of a more statistical mechanics condensed matter bent, probably I would go there. But right now, what I wanted to do was produce a number which would be useful for astrophysicists.
May I ask another one? So, when you have these kind of late time behavior from cascade, usually it happens in a very strongly coupled system. But here, this is a very weakly coupled. So, what is causing this cascade?
Yes. Yes. So this is an excellent question, and so this is beautiful, right? That you have a bunch of neutrinos which are famously weakly interacting, and yet you have this unusual collective behavior, which is kind of reminiscent of strong interactions. The point is that N is your large density. That's what that's what provides you the pinning. So the picture really to have in mind is this, that ordinary neutrino oscillations is spin precession around a magnetic field. Collective neutrino oscillations is a lot of spins which are precessing not just under the influence of an external magnetic field, but under the influence of all the microscopic spins which are themselves changing, and that can have very interesting dynamics, including fast dynamics that I told you about. So that's
Thanks
the origin.
again for the very fascinating talk. You are always inspiration for us.
Thank you.
Thanks.
So when you, what I understand is when we talk about collective neutrino oscillation, their frequency, they all are oscillating with same frequency.
Yes.
So what about their relative phases? So is that constant? I mean, is that or?
Yes. So if I understand, you are saying that collective neutrino oscillations, all the different neutrinos with different momenta energy are oscillating with the same frequency.
Yes.
What happens to their relative phase?
Yes.
Yes. So indeed, if they were perfectly collective, the relative phase would be 0 throughout. What I showed you towards the later part of my talk is that the relative phases do not remain 0 ad infinitum. Eventually, these relative phases start growing and things get mixed up. Once relative phases are growing to order 1, and unless you are measuring very, very precisely, effectively what it means is that you lose coherence. and that's what exactly happens. Yeah.
Thank
So collective, you have to understand, is a approximate description. It's approximately collective. All right, collective to begin with, and then becomes less collective later on.
Thank you.
Great question. Thank you.
Towards the end, you showed these elements that are produced, and somehow it stopped at around A equal to 200. Why was that? I mean, we know that there is uranium, and perhaps even other elements are produced, like californium 252 and whatnot. So why is it that just computationally this is a difficult thing to do? Or?
I don't know.
For instance, that yellow or the orange curve, that goes up to maybe around 240 or something, but there's no data point there. Or is it just a lack of data?
No, so these three curves are, so this red is, I think, I'm not sure if it's data or calculation, but this is what happens in a solar metallicity star. Okay. And the green and the yellow are calculations in a merging neutron star.
That's right. So they show very different behavior for the heavy.
Yes, so it depends. So that's why I think what they're showing is that the abundance is very different depending on the neutron.
In fact, it is also very
abundance.
different from the these two computations.
Yeah, because one has this neutrino mixing and the other does not. And so
So the relative difference I can understand.
Yeah.
But those other red points.
Red,
that's still very different, and this is
very
a log scale, right?
Yes.
So this is like a factor of 100 or 1,000 more.
Yes. Yes.
So there's still a long way to go in understanding. Is that a correct statement?
So I have to admit my ignorance about I never usually do this. When I show something, I always know what I'm showing. I have forgotten what these red points are.
I mean,
no.
The rest of it looks good.
No. Your question is valid. I should have been able to tell you what these red points are. I've forgotten. I don't know whether it's data or a calculation, but it's the abundance in a solar metallity star. I don't remember whether it's data or calculation.
No, the other is a more naive question. You said that you do a 1 + 1 + 1 dimension calculation. Now, is there any clue as to what might happen if you do the real thing?
Yes, so there are people who have computed. Yeah, so in fact,
will some features change dramatically, or maybe less so?
Yeah, so this is, I'm happy to report that basically nothing changes. So this is the thing that, once you have taken care of some key crucial physics, after that, changing things, going to 3 dimensions doesn't change the problem that much. Now, in this particular case, as it happens, once you go to 1 + 1 + 1 dimension, you have it. So after we did this calculation in 2018 or so, to 18-19 or so, there have been groups in Berkeley and others who have done calculations in 2D and 3D. There has been a recent code comparison paper, including Shommo. I am not involved, and all the results line up with each other basically. So
you captured the essence of the.
So this is basically what you get. Of course you can improve things. If you want 1% precision calculations, you should do a calculation in 3D. But to get the basic idea, I think this is enough.
Yeah. Normally, when you do oscillations, the nature of neutrino doesn't come in because it's the same for Dirac and Majorana. However, the collective term, because it involves the density, it should make a difference whether it is Dirac or Majorana, isn't it?
Technically, maybe. In practice, not quite, and it takes to the other question you had asked about mean fields.
Okay.
So this calculation is done. So sorry, this answer is a little technical, but because you asked. See, you should be a little worried that I have a calculation, which is supposedly a quantum mechanical calculation, where I have both space and momentum being specified. Okay, so let's just go to that equation, and then you see this is a local equation. It's an equation at each point in space and time.
Yeah.
And I'm telling you that the momentum is p. You should cry murder. This is wrong, right? So what am I doing? You can't specify space and momentum, spatial coordinate and momentum at the same time. What is being done is that you take your phase space and discretize it into cubes that are larger than the de Broglie wavelength of the neutrino. So, you make the kinematics of the neutrino completely classical, and you treat the flavor evolution quantum mechanically. So, this is the Wigner transformation. Okay. Now, we are looking at the quantum field theoretic expectation values of things like A dagger A and B dagger B. We are not going to look at things like A dagger B. If we did, helicity changing effects would be important and those other factors would be important. But those are terms that are suppressed by small parameters. In principle, that does not make them insignificant, because you can have an instability that makes something grow. People have looked into that. So far, I don't think there is anything that shows that if you have a Majorana versus a Dirac, something totally bizarre new thing would happen. I haven't seen anything like that, but I also must admit that this is not something that I have studied quite deeply. My expertise is kind of limited to these Wigner function based treatments, ignoring helicity correlations. Otherwise, yes, what you're saying could be important.
Some degrees of freedom may be different, no? So you will have to
Yeah, so you would not be just able to work with the rho and the rho bar separately.
Yeah.
You would have to worry about the, a 6 cross 6 matrix
exactly.
with the off diagonal 3 by 3 matrix, which involves this A dagger B's and,
Correct.
So,
Using massive neutrinos anyway,
yeah.
degrees of freedom will be less.
Yeah. So that
Then the new bar densities will come in.
yes.
Yeah, differently. Huh?
Yes.
Ah, okay.
The collective terms will change.
Yes. That's a technically difficult thing to do. So,
So, you make the statement that even if I start with a very small mixing angle, there can be very fast and very large change in the survival probability. So this very small mixing angle is because of the environment in which the neutrinos are created, and hence MSW.
could be either. So, imagine that theta 13 is 10 power minus 4. Imagine a universe. And even in vacuum, let's say if you have lots of neutrinos, vacuum is in a box with no background matter, but lots of neutrinos, all of this goes through. Or imagine that you have theta 13 of whatever 10 degrees, which is not small according to me, and you put background matter, which basically shrinks the mixing angle by a factor of 10,000. That's the typical density in the star, and so the suppression of mixing angle is approximately by a factor of 10 power 5. So now your effective mixing angle is really small,
Okay, yeah.
and now apply the collective term on top of that.
And this is probably silly, but in one of the earlier plots, there's either probability or average probability, which is 1 to minus 1.
Oh, no, you are right. I sometimes take liberties, in the interest of not having to precisely state what I am doing, rather give you a feeling for what the correct thing is. So, but you have caught me, so I will now have to explain. So you are right. You are somebody with an eagle eye. Here it is. This is the one, right? Right?
Yeah.
Yeah. So these are fine. So what is being plotted here is the probability for survival, and this is all positive. So we don't have a quarrel here. These two are not probabilities. So they are the z component of this spin.
Okay.
And in this case, the spins are normalized to 1, so it goes from 1 to minus 1. In this case, the spins are normalized to something like 4, because it was, as you noticed in that calculation, basically PL plus PR plus PL bar plus PR bar minus a small term. So that would normalize to something like slightly less than 4, and that's what this is. And so everything is okay, but forgive my rough language.
So, and towards the end, so you're showing probability as a function of the velocity. So is this like a frame dependent?
Okay, so this, so what I was showing is the survival probability as a function of the neutrino velocity or the neutrino momentum. So imagine I could show you survival probability as a function of neutrino energy, right? So this no one balks at. Of course, low energy neutrinos, adiabatic, high energy neutrinos, non-adiabatic, you can do all that. But it also depends in this case on the velocity, which direction it is going. And that's what I'm showing you, that the survival probability depends not just on the energy, but on which direction it was traveling at. And how does direction get defined? Relative to the normal from the neutrinosphere, roughly speaking. So that's what defines your direction.
Thank you.
These are two basic questions. If you start with not with the flavor states or with the mass eigenstates, this analysis will change? And the second one is, it has to saturate all this exponential thing which you showed that it's going to saturate at some point.
Yes.
And which property is making it to saturate here?
Okay, very good. All right. So the first question was that if I don't start with a flavor eigenstate, but I start with a mass eigenstate, will any of this change? Well, so this is a very interesting question actually, because for ordinary neutrino oscillations, you can define the mass eigenstate. Here, defining the mass eigenstate itself is very hard, because at each point you have to actually diagonalize this last complicated collective term, which is equivalent to solving the entire equation. So how do you even know what your mass eigenstates are? And the funny thing is that even if you could do that, the evolution is actually non-adiabatic. So the things don't stay in their own mass eigenstates. Usually, I don't know if you are already familiar with adiabatic and non-adiabatic evolution or not, but in case not, you ignore these comments. Main point being that in ordinary neutrino oscillations, starting with a mass eigenstate would not lead to oscillations. Of course, you can ask, how will I start with a mass eigenstate? You can't. Basically, neutrinos are always produced as flavor states. But let's say somehow you could produce a mass eigenstate, it would not oscillate. Okay? But for collective oscillations, it's difficult to even define what the energy eigenstate is without actually just fully solving the problem. You have to just, you have to know what the eigenstates are. Okay, that's the first question. The second question was, what is making the exponential rise saturate? I had said at the very beginning, exponentials saturate because some resource runs out. So that, which means that there is some constraint. Like the total number of people in India is 1.4 billion or whatever, and so more than that number of COVID cases cannot happen, unless of course there are reinfections, or whatever. The number of transistors on a chip is limited by the number of silicon atoms available to you or something, right? So these are constraints. What's the constraint in this case? The constraint is that probability must be conserved, and there's unitarity. So when I'm going from one flavor to another, the maximum that I can go to is 1. I cannot grow beyond 1. I can have 100% flavor conversion, but no more than 100%. And so that's the ceiling. So I start with something very small, I grow exponentially. Roughly by the time I get to something of the order of 0.1, I'm very close to the ceiling, which is at 1. And that at that point I saturate. I can oscillate a few times, but then eventually I will saturate. Did I roughly answer your questions?
Yes, the reason of my first question is, instead of 3 eigenstates, if you add some extra sterile state,
yes,
whether this calculation can be extended. That's why
of course. But then that is independent of whether you start with mass eigenstates or flavor eigenstates. You can do it with 4 flavors if you like, yes.
Are there any more questions? Can't see any hands. Ask us.
Will the presence of sterile neutrinos affect this in any way?
Yes, it will. The only reason we don't do it is this is already a complicated problem, but okay. But yes, it will. Main reason it will is that sterile neutrinos do not feel the impact of the background matter. So that mixing angle, roughly speaking, especially if there are more than one sterile neutrinos, then the angle between these 2 sterile neutrinos is not going to be suppressed. That's one of the key things. Even otherwise, you know, roughly speaking, fast oscillations is going to lead to flavor equipartition, 1:1:1. We expect that would become, so we should say 0.3, 1/3, 1/3. With sterile neutrinos, we would expect that to become 1/4, 1/4, 1/4, 1/4, if there are the right kind of momentum crossings. Okay, that instability must exist. You know, you must have that door to go to the sterile. Otherwise, the sterile just stays, you know, living its own hermit life. So, modulo these little, but yeah, short answer is it will affect things. It's an interesting question.
No, so reversing it, from observations, would it be possible to infer, yeah, that there's something fishy going on?
Yes, but for that you have to first calculate what will happen with sterile neutrinos, which is, you know, yeah, what you expect. These are all worthwhile things, but you know, finite time, finite
resources. Yeah. So it's, the thing is, when you turn on your matter effects, you have new scales.
Yes.
In the problem.
Yes.
And if your electron density starts to match your neutrino density in some universe, then you will get even more interesting results, right?
Right. Now, this is an interesting question also. You're basically saying that for the purposes of this talk, I had basically ignored the entire story of this MSW matter term, the electron. All that I did was I said that, well, choose a very large electron density and use that to make the mixing angle very small, and after that forget about the electron density. That's what I have done. Could there be interesting interplays due to the second term due to MSW effect and the third term due to neutrino collective effect? The answer is yes, people have looked into those. So I have also, one of the things that it does, and so this is the one example that I will give. So imagine that the electron density drops from a very large value to a very small value, while the third term is incredibly large. So what the third term does is it makes all the neutrinos behave identically. Now what it does is that the MSW effect, which will happen because now the electron density has dropped below the delta m square value, will be made collective, that all the different energies will undergo an MSW transition together at the same density with the same adiabaticity. So this is a collective MSW. So this is the kind of thing that you can do. So, and
sorry, then right in the beginning, when you have neutronization of the core and your electron density drops, you actually must see this, right?
Yes. So this is indeed one of the things that we did, 2008.
Okay. I don't remember clearly.
So the oxygen magnesium neon supernova, whose electron density drops like that, where we predict that such things will happen.
Sorry, I must have forgotten that paper.
Oh no, so no, this is the kind of thing that, you know, you would think about immediately once you see these terms.
Right.
And it's very interesting. This is a huge amount of rich phenomenology, depending on which, you know, whether you're looking at one kind of supernova or neutron stars or another. So this is the beauty of, you know, having to apply neutrino physics to astrophysical systems. You have a zoo.
Yeah, amazing. So where is Arijit? No, there's, okay. Oh, there are, okay. So yeah, I think it was a fantastic talk. Thank you very much, Basudeb. I think everyone's enjoyed themselves. And as a rich reward, you will get tea outside the auditorium. Huh? Oh, we get high tea. It's not just tea, but high tea. And in fact, I think after this, I forgot to mention, and it's obvious now why, but I should have also mentioned that recently, well, before COVID, but I would think of it recently, Basudeb was awarded an ICTP prize in memory of S. Chandrasekhar for the kind of work he does, and I think you can see he has richly deserved it. So I forgot to mention that while introducing him. So that's another point. So thank you, everyone. I guess we joined to.
Thank you. It's a pleasure and it's an honor to be back here. And if you have any other questions, please feel, especially students, please just email me or whatever. I'm here for the whole day. Tomorrow morning I'm leaving, but please feel free to contact me. So you'll be having? I'll be outside. I'll have tea, and I'll be here as long as you want. I'm sorry. I'm in room 315, but I'll probably be here.
Okay, fine.